All right, so continuing where we left off last time, we were talking about algorithms and algorithm analysis, and we did this motivating demonstration where we found that some operation was really, really slow when we switched over to a linked list. And the reason for that is that the basic get the ith element operation, the cost there is much more when you're using a linked list. And that's because you start at the beginning all the time, right? You start at the beginning of the list, and to get to the ith element requires I traversals to to that node. And we summed those all up, and we found that there were about n squared total traversal operations. In contrast, if you just use the array list, you can use random access, and you can immediately jump there with just a memory offset computation. Right, you have a memory address where the array starts. You know that you want to go I elements over, and you know how many bytes each one takes. And so I times number of bytes plus this initial address, and you jump there, and it's immediate basically. At some point, I timed this on a quiescent machine, that is a machine that wasn't running OBS and QuickTime and a whole bunch of other things at the same time. And then I ran this experiment multiple times. And in the x-axis here, we've got the list size in thousands. So 1,000 thousands, that's 1 million elements. And then the y-axis here, we have the time that it took to do those operations, to sum up all those numbers. The blue graph here is the discrete. We went by increments of like 50,000 or something. This blue graph is showing those results, right? Now, the red graph is what's called a regression. So you posit or you think, okay, well, that growth rate, that looks kind of quadratic because that's what a quadratic function looks like. And so what we'll do is we'll try to come up with a quadratic, not a quadratic formula, but a quadratic equation that kind of fits that data, right? And so at some point I did that, and the red line there, I don't have, I guess I have it here, right? Looks kind of like this, okay? Now there's a very small coefficient out front here for the n squared, and that's because when you're running on a computer, every single traversal takes a very, very small amount of time, right? Each traversal could be a millionth of a second or nanosecond or something like that. But it is still a quadratic equation here, right? It's still going to grow quadratically. And the correlation coefficient there was almost perfect, like a 0.994. A perfect value would be 1. In other words, it would fit that graph completely. Now, we've already timed this before with like 1 million, and if we look at the result over here, it'd be about 500 seconds or so, right? That would be about 10 minutes, and I'm not going to run the experiment again. But what we are going to do is we're going to map this out and think about larger and larger inputs, because that's what we care about in algorithms and algorithm analysis. As we process more and more data, as we process bigger and bigger data, what is the behavior of this particular algorithm? And if you map this out to, say, 10 million instead of 1 million, then you get in the order of 17 hours, right? Now to do that, all you have to do is take 10 million and plug that in for n in this equation, and that gives you the number of seconds, right? Or maybe milliseconds multiply by 1,000 or divide by 1,000, something like that. But in any case, you're on the order of 17 hours now instead. With 1 million, it was 10 million, or it was 10 minutes, and now it's blown up to hours. Right? If you go up another order of magnitude, if you go up to 100 million, you'll find that it's out at 74 days. Right? So these things are going up by not orders of magnitude, but orders of magnitude of orders of magnitude. 10 times bigger means it's 100 times slower. If we go up to 1 billion, right? What's your estimate now? Not just days, but now decades. Right? In fact, it's 20 years or more. Right? This is not at all acceptable, right? 1 billion elements, that's less than 4 gigabytes of data, right? Are you going to wait 20 years to process 4 gigabytes of data? Absolutely not. In contrast, if we had used an array-based list, I wouldn't even be able to graph it here because the graph would essentially be coincident with the x-axis there. It wouldn't even be perceivable here, right? But it is linear behavior. It would still be a linear function. It still grows, but it grows at a much, much less rate. Right? Now, for 1 million, at some point I observed that it was 0.0009. Right? At 10 million, you would expect it to be about 10 times slower because it's linear. Right? And I measured it to be that. Right? If at 100 million, that's going to be 10 times slower. It's still only 0.3 seconds. Contrast that with 100 million with a linked list, and it's 74 days. Right? Now, at 1 billion, it becomes really apparent why you shouldn't be doing this. Right? That 1 billion, it's actually 3 seconds instead of 20 years. Right? Still noticeable to humans now, right? 3 seconds, but processing 4 gigs of data, that's reasonable. 3 seconds. Right? So the takeaway from here is that data structures and your choice of data structures and the situation in which you use a particular data structure, it's important. Right? Now let's come back over here and fix this code here. Now the fix is not to always use an array list. Right? There are situations where an array list is actually not the correct choice. For example, if you're doing a queue, right? An array list would not be great because you are always shifting things over. In fact, any operation that removes something from the beginning of the list and has to shift everything down, it's going to have the same poor behavior as a linked list in this situation. Right? So it's not always just always use a linked list or always use an array list, right? It depends on the situation. The real fix here is not to write code like this. This is code that any boot camper or CS1 student would write, right? But it is absolutely incorrect. Right? Let me go ahead and fix this. And just in case you think that this is a made-up example, No, several years ago, I took this as an example from a colleague that said, hey, check out this code base. And I pulled it up, and the first piece of code that I saw was this. It was Java code. I said, no, that's terrible, right? And then looking at the rest of the code base, no, it's terrible, it's terrible, it's terrible, right? For various reasons. Right? Now, the real solution here is not to use a traditional for loop. It's instead to use a enhanced for loop for an int x in the collection numbers, right? Do not use the get method here, right? Because it's a list. It could be a linked list, which means that this would actually be expensive. Now, the enhanced for loop here is the better code, right? First of all, it's simpler, but also it's more efficient. It's more efficient because it does the same trick that we did when we did our own linked list. When we had to get the previous and the current and the next in order to shuffle things around, I said, we don't want to do this 3 times. Get the ith element, get the I plus 1th element, get the I plus 2th element, or whatever, right? I said, let's do that once. Well, let's make the investment to get the ith element, and then instead of starting at the beginning and get the I plus 1th element, we'll just go next one more time. This enhanced for loop here is doing exactly that. It doesn't start over at the beginning of the list every single iteration. Instead, behind the scenes, it's keeping track of wherever you are in the current node. And from the current node, it just goes one more traversal to get to the next node. Now you'll see here that if we bump this up to 1 million, right? Whereas before it was taking like 10 minutes by our estimation, or 20 minutes last time, right? Now it's almost instantaneous, right? Much, much improved here, right? And I didn't change the data structure here. Instead, I used the data structure correctly, right? And again, that's the difference between a boot camp coder and a computer scientist. They know what they're doing, and they know what's going on under the hood. They know when to use something, when not to use something, or when to use something differently, all right? All right, so hopefully that motivated the discussion. Now what we need to do is we need to actually formalize all this. How do we go about designing an algorithm and then analyzing the algorithm with respect to the input size, okay? It should be clear that most algorithms require some sort of resource, some sort of computational resource. The most obvious one is, of course, going to be processing, or CPU or GPU time, right? Processing, there we go, right? And that translates into wall clock time in some instances, right? Because it's 3 seconds or it's 20 years, right? From the processor perspective, it's the number of clock cycles or the number, whatever whatever a processor is doing, right? And you'll see that this can actually be different in your lab next week when you do some parallel and distributed computing. You'll find that inserting a lot of people into a database takes 10 minutes or something like that, inserting 1 million records. But then what happens if you split it up among different processors, right? What if you were inserting 8 million records and it took you a minute to do that? Well, if you had 8 processors instead, each only one doing 1 million, right? Now it's 8 times faster. If you were using 16 processors, now it's 16 times faster. With a GPU, right? That's a completely different story there. You have hundreds of cores there, or thousands of cores in a GPU. And now things are sped up thousands of times, right? Of course, a GPU is not a full CPU, but it's good enough for a lot of stuff out there. The other obvious one is going to be memory, right? Garmin has often visited us, and so I always tell the story of Garmin. They come in and they talk about engineering problems. And one of the problems that they talk about is sometimes you have to have a trade-off. For example, with Garmin, they do embedded systems, right? They do GPS stuff for airplanes. And one of the examples that they pointed out was they actually went with a slower sorting algorithm, like a bubble sort or something like that, because it was less memory intensive than, say, quick sort or merge sort or sorting, faster sorting algorithm. And there was an engineering concern. With an embedded system, you are constrained by the amount of memory that you have on that embedded system rather than on the processing time, right? So they went with a different engineering solution, optimizing for memory instead of optimizing for CPU time, right? What's another computational resource, especially now that we've got these huge data centers, right? What do you think of as a computational source? Yeah. Oh, okay. Well, I would put RAM under memory, right? Right. Yeah, this is still the same as memory, right? Yeah. Okay, so secondary storage, right? Storage, right? We'll come back to that one here in a second, but I would put that under memory as well, right? At least for now, right? Big giant data centers, they're known for. In fact, I saw an article the other day that says that they're creating heat. They're creating heat sinks in the middle of wherever they're located. They will increase the environmental heat by 16 degrees, right? And that's because they all consume massive amounts of power, right? Or if you're running a Bitcoin operation or something, right? It actually probably, given the price of Bitcoin, I don't think it's worth it anymore to mine unless somebody else is paying for the power, right? The power costs now exceed what you actually get out of mining that stuff. Another one would be network bandwidth or throughput. You mentioned hard drive or secondary storage, right? It is still faster and cheaper to load up a semi-truck full of hard drives and drive it across the country and deliver all that data. That is faster than sending an equivalent amount of data over the fastest network that you can think of today, right? Network bandwidth, is still a bottleneck for computing, right? Input-output being the other one, right? So networking is still very, very slow. And as you'll see in next week's lab, like I mentioned, if you do it off campus through a VPN, right, it took me like 10 minutes to get all these records, a million records into my database. If you do it on campus, right, you're way closer, your network latency is far smaller than it gets done in like a few seconds or something, right? So networking is definitely a computational resource. If you're when you get into 231 or 230, whichever one you take, or maybe you've already done some electrical engineering, you start designing actual circuits, and circuits are a form of algorithm. The most expensive thing with respect to circuits are the number of wires or the number of gates, because that translates directly to power consumption, right? If you've got a longer wire, right, then that's going to be a latency as well. It takes more power to send that over a longer wire than it does a shorter wire, and also there's a latency there, right? It's not at the speed of light unless it's like optical or something, but it's significantly reduced because of impedance, right? Also, the number of gates, OR gates, AND gates, NOR gates, right? That the more gates that you have, the more power consumption and the more time it takes for those gates to settle into a solution, right? One thing that almost nobody ever thinks about is the opposite of this: idleness or utilization, right? Something has come along in the last 10, 15, 20 years to solve that problem called virtualization. You may or may not have been exposed to that kind of stuff. Like I know a lot of people have had virtual machines, right? It doesn't make any sense for a small organization to pay for their own hardware, right? If you're just running some website with a couple of hundred users, why spend so much money in $5,000 in equipment and several $100s in, or several $1,000s in software to run that equipment, et cetera, and power, right? Where it's sitting there idle most of the time. So what you do is you shop that out, or you buy one piece of equipment and then you run 20 virtual machines on it. Now all those small operations, now it has a high utilization. It's not sitting there idle anymore. And it's 1/20th of the cost because you're all sharing that hardware together. Right? This is what Amazon Web Services is based on. Right? It's now enterprise level where you don't have to pay, you don't have to even collaborate to get your own virtual machine hardware. You just pay Amazon to do it all for you, right? So all of those are very, very important questions, but they're engineering questions, right? They're not algorithm questions, okay? These are important engineering concerns and considerations when you're actually building a system or you're designing a circuit or something like that, right? They're not algorithm questions. Algorithms are thousands of years old. One of the oldest algorithms that we have is the Euclid's GCD algorithm, which is almost 3,000 years old, right? 2,600 years or something. Computers are only decades old, right? Just the mere fact that computers were invented and developed in the last 50 years doesn't mean that those algorithms that were invented thousands of years ago are now suddenly fast, right? It just means that we can process more data in a smaller amount of time. The number of steps each one of those algorithms took is exactly the same as 3,000 years ago. Algorithms don't change. The behavior of algorithms and the efficiency of algorithms are invariant across time and across the hardware that you use. If you upgrade your hardware and now it's twice as fast, that doesn't mean that the algorithm is twice as fast. It's still doing the same number of steps. If it did 5 steps before, it's still doing 5 steps on this upgraded hardware. It's just that the upgraded hardware can do those 5 steps in half the time, right? And so from a theoretical perspective, what we need is an abstract notion of what an algorithm resource is, right? It's not tied to a particular computing model. It's not tied to like a computer language, a piece of hardware, or whatever, right? What matters is the performance as you process more and more data, right? What matters is the performance of a particular algorithm with respect to the input size and how the performance behaves as n tends towards infinity. In other words, you start out with 10 million elements. What happens when you go up to 100 million elements? What happens when you go up to a billion elements, right? Those are the questions that we want to answer, right? Algorithms are independent of any of those concerns, right? Again, algorithms are thousands of years old. Euclid's GCD, let me give credit there where credit is due. Euclid's GCD algorithm, right? That's almost 3,000 years old. And it doesn't suddenly become efficient just because we upgrade our hardware. When Euclid was doing this on a piece of papyrus 3,000 years ago, right? He did the exact same number of steps that a modern computer would be doing, right? The computer's still doing the same 5 steps that Euclid was doing way back then, right? Instead, individual operations, like for example, add, multiply, compare, those become faster on modern hardware or as you upgrade your hardware. But the number of operations still stays the same, right? The rate of growth is an invariant, right? Again, algorithms 3,000 years ago are going to be the same 3,000 years from now. If you go into the future 3,000 years from now, and they've all got these super massive quantum galaxy computers or whatever, I can guarantee you they will still be doing the same number of operations that Euclid did 3,000 years ago, right? Larger inputs should lead to slower performance. In other words, more resources. That's the notion that we want to capture, right? The larger and larger inputs means that there are going to be more and more resources and means more and more time, right? More and more memory, more and more operations, whatever you want to quantify as your engineering question that we started out with here, right? More power, more network bandwidth, whatever, okay? All right, to start, what we're going to have to do is we're going to have to divorce ourselves from Python, divorce ourselves from C, divorce ourselves from Java, and develop in what is called pseudocode. All right, so pseudo means fake, and code means code, right? So fake code, right? What I'm about to give you is a dictionary definition. This is not the mathematical definition. But an algorithm is an unambiguous sequence of instructions for solving a problem. If you were to look this up in Webster's, that's about what it would be. Unfortunately, that's not enough for theoretical computer science, and it's not enough for mathematics. Instead, what we have, the mathematical definition of what an algorithm is a Turing machine. And that's equivalent to, say, lambda calculus, and it's equivalent to a couple of other mathematical models. You'll eventually learn about those in a theory of computation course if you take one, right? But for us, the dictionary definition is going to be enough, right? What it is not a Java program. It is not a method. It is not a function. It's not a snippet of code, right? What it is its own thing, okay? The general outline looks kind of like code though, right? But it's not, right? Good pseudocode, right? Makes use of plain English, right, when possible, makes use of mathematical notation, right, provides necessary details without unnecessary details, right? We call this I don't know how common this is, but this is Goldilocks, right? Why do I call it Goldilocks? Not too hot, not too cold, just right. The porridge is just right. You don't want to put in too many details. You don't want to put in unnecessary details. You want to put in enough details that when somebody says, okay, now I need to actually write this in Java, right? You have enough details that you can translate it to Java. Now I need to write this in Python. You have enough details that you can write it in Python. And you don't have unnecessary details like, oh, well, if you're using Java, you need to use an array-based list because of whatever, right? No, those are not necessary details, right? By the way, there are no rules for pseudocode. There are only guidelines. I can't give you rules. Right? What would happen if I gave you a rule for pseudocode? You have to follow it this way. You have to write it this way. What's that called? It's a code. It's a programming language, right? That's what Java is. That's what C is. It is a bunch of rules, syntactic rules for writing a program that then gets translated into machine code, right? So let's go ahead and take a look at an example, right? Called linear search. There we go. Okay. And for that, I'm going to come over here and start typing it out. I'll start writing it out. Okay. All right. With good pseudocode, you generally want to clearly label your input and clearly label your output. So what I'm going to do here is I'm going to say what my input is. Right? Now what we're going to do is, if you were to do this in Java or if you were to do this in C or something, then you would have to say, well, here's an array and here's a key. I want you to search that array for this key and return the index at which you found it. Right? That would be way too, way too specific. I want to keep this generic and general. So what I'm going to do is I'm going to say that this is not an array, but a collection. Right? And I'm going to label it as A. And also I'm going to label each element, A1, A2, ... AN, comma. There we go. Now, did I say that this was an array? Did I say that this was a list? Did I say that this was a set or a map or any specific data structure? No. It's a generic collection of stuff. Also, did I use zero indexing here and I go up to n-1? No. That's a computer science thing. Every self-respecting computer scientist will start at 0 because that's how most indexing works. But mathematicians, we're now in the realm of mathematics here, they always start their indexing at 1, right? The counting numbers, right, so to speak. Okay. By the way, there are programming languages out there that do not use zero indexing. Kind of weird, but yeah. MATLAB is one of them. I think somebody else pointed out the other day that Lua is another one. Has anybody done Lua stuff? Like Roblox programming, basically? That's all I know. That's all I know that it's used for. Is Lua used for anything else? Is it what? Like Gmod mods. Oh, what's Gmod? Gary's mod, you mean? Yeah. Oh, Gary's mod was written in Lua?
No, like if you make a mod.
Oh, you're making a mod for the mod.
Yeah.
Okay, I never knew that was a thing, but great. All right, so there are languages that start out with 1, as weird as they are. Right? And I'm going to label this as a key. Okay. Now, again, did I say that these were integers or doubles or strings or whatever? Nope. I'm keeping it general and generic. You can translate that to whatever you want. Right? Then I'm going to label the output. Right? An element, AI, in A, such that, and again, use a plain old English here, right? Interleaving it with mathematical notation. So the A sub I is equal to K. Now again, did I say what equality means here? If it's a number, then that's pretty straightforward. But if it's a string, that string is equal to that string, ignoring case, or is it case sensitive? That invoice is equal to that invoice. Right? There could be a lot of things that you would say equality on there. The database ID, the UUID, the natural key, the total, right? The salesperson, right? There are lots of ways of thinking about equality that you can put into a comparator, right? All right, we'll come back, but because we're not done with the output up there. But I will start writing my algorithm right here. It's always good to number your lines so you can refer to them. The first line here is for each element AI in A. Nice English here, right? Now there are some the languages that have the keyword for each. It's all one word. PHP is one of them. Python, Java, and C, they don't have anything like this. They have just traditional for loops or enhanced for loops. Or in the case of In the case of Python, Python doesn't even technically have traditional for loops. A for loop in Python is simply iterating over a collection. For x in A. If you want a traditional for loop that runs from 0 up to n minus 1 by increments of 1, you have to call this other function called range, right? So this is not Python, this is not C or anything else like that. We're using plain old English here, right? A sub I in A, right? If A sub I is equal to K, and again, I am not specifying that what equality means here. There's line 2. Then I will output. I'm not returning, I'm not exiting, I'm not doing anything like that. I'm literally outputting A sub I, right? And that's line 3. Another thing that I like to do with my pseudocode at least, again, these are guidelines. I can't give you rules to follow. So if you don't do it the way I do it, then you're not violating the rules. But the way that I like to do it is I like to put in vertical lines with a little foot outside there, right? And I'm going to do the same thing for the for loop over here. It's got to be straighter there. Okay. I'll do the line, and then I'll do that guy. There we go. Okay. And the reason that I like to do it that way is because there's no way that you could ever mistake this for Java code or Python code, right? There is no programming language where you can literally draw this vertical line here. Right? In programming language like Java or C, you would use opening brackets and closing curly brackets. In Python, what would you do? Python, you would still use the same indentation, but what belongs right here in Python? Pythoners? Oh no? A colon, exactly. Right? All right. Are we done? Right? What happens in the case that we don't find what we're looking for? Nothing matches that key K. Right? If this were Java, you could return a negative value, right? Where you could return a negative index value. If this were Java, you could throw an exception, right? If this were Python, what could you do? Python, you could also return a negative index if you were returning a negative index, right? But instead of returning null in Java, what is null in Python? None, right? I'm not going to do either one of those. I'm going to output, again, I'm not returning, I will output phi. Phi is a nice mathematical notation for nothing, right? Sometimes it's used for the empty set. Sometimes it's used for other mathematical things that have an interpretation of nothing. So I will put that into my output statement up here. Phi if no such element. Okay? Great. There's my pseudocode. Now, if you're interested, here's what it looks like. Come on. All right, fine. Insert from files, iCloud, there we go, algorithms, and where's my linear search? There we go. All right, so there's the equivalent of what I just did, but instead, I wrote it up in LaTeX. Now, LaTeX is a typesetting system. If you know it, great. If you've been using it for your design documents, great. It's not required for this course. It's certainly not required for a career in CS. It's something that looks nice, right? It looks way better than Word. But at the end of the day, you're not going to use it in industry. I've never seen anybody in industry use it. It's an academic thing. If you were to write up a paper, a research paper, then you would definitely want to use LaTeX. Otherwise, you'd be laughed at. Like, this is disgusting Word stuff here, right? But in any case, what we've got the same similar elements here for each keyword: vertical lines, right? Mathematical notation, generic statements like this, right? Now, if I were to use LaTeX here, I would of course have to adhere to their guidelines because it's a compiled language, right? But in fact, it's Turing complete. You can do anything in Python. You can do anything in LaTeX if you want to. But there, that's it, right? Okay. All right, we'll come back to that because it looks much nicer. But what I want to do is now that we've got pseudocode, and we'll look at a couple of examples and develop a couple of examples as we go along here. What I want to do is I want to actually analyze this now, right? So how good or bad is a particular algorithm, right? And to answer that, usually what I do is I give a 5-step process. It's not my 5-step process. It's basically an established 5-step process. One is you want to identify the input. If you've already written good pseudocode, or if good pseudocode has already been provided, that's pretty straightforward. Right? For example, over here, this is good pseudocode. Right? But there are situations in which you do have to be careful, because it seems like there are actually 2 inputs here. There's the collection, and then there's this key sitting over here. So we have to decide which one of those to look at. Right? We'll talk about that in more detail here in a second. Then we identify the input size, and we give that a label. Usually it's n, okay? Because n is usually the value associated with the input size. Then what we do is we identify the elementary operation. This goes back to our engineering questions up here. How much CPU time does it take? How much memory does it take? How much power does it take, et cetera, right? We don't want to look at any of those particular values. We just want to look at an elementary operation. There could be more than one answer, right, leading to more than one way of analyzing the algorithm. Usually there's going to be a straightforward or an obvious answer, but it could be a plus, an addition, it could be a division, whichever one is the most expensive. But that's also part of the art. Once we've done those 3 things, right, then we need to determine how many times the elementary operation is executed with respect to the input size. That's the real algorithm analysis right there. 1, 2, 3 is just the setup. Then here's where the real work occurs. Then finally, we provide what's called a big O or big O analysis of this. Right? And we'll talk about big O towards the end, but what I want to do is I want to focus on 1, 2, 3, and 4 today. Okay? All right, so the first step, identifying the input. Right? Again, if you've written good pseudocode, this is generally done for you, right? Or you've done this as part of writing the pseudocode. However, in some cases, it is less clear. Right? So for example, what if you have multiple inputs, okay? Keep things simple, Keep thinking simple, right? Focus only on one. Because you don't want this to be a multivariate function, right? Ultimately, you're going to come up with a function that determines the how many times the elementary operation is executed, right? You don't want n and m and l and x, right? You want one thing. You want n, right? So keep identify the most relevant one, right? You choose the most relevant input to the algorithm, or the one that has the biggest impact on the performance of the algorithm, etc. For example, what about linear search? Right? Let's go back to the pseudocode over here. I actually have 2 inputs. Right? I have A, and I have this E sub k over here. And by the way, we actually have n inputs, but it's all part of one collection. Right? So which one of these is going to have more impact and more influence on the behavior of this algorithm? Is it going to be the one with n elements that we iterate over? Right? We do it n times until we don't find what we're looking for, or we get unlucky and the last element that we look at, that's the one that we find? Or is it going to be this single E sub k here, the single key element over here? It's definitely going to be this one right here, right? Because as the collection grows, if you go from 1 million elements to 10 million elements, obviously it's going to take way more time to process all that data. But over here, the key, that never changes. There's only one element over here, right? If you go from 10 million to 100 million, right, the key stays the same. There's only one. This one is going to influence this for loop right here, and that's the one that we choose. All right. So with linear search, we choose the collection because its size affects the performance more than the single key effects. Okay. Another one, say Euclid's GCD algorithm. Let me come over here. I don't have that available, but basically we can look at an example here if I can do the math in my head. Right? I don't know, GCD. There's the greatest common divisor. of 1024 and 52. There we go. So there's an algorithm here. What we would do is you would divide the larger one by the smaller one and get the remainder, and then you would divide that, subtract, find the remainder, and then keep finding factors basically. Now I chose this because 52 in my head here is equal to 2 times 13, correct? All right? And 1024, that's equal to 2 to the 8th. So there are 2 2's over here and 2 2's over here. So what is the greatest common divisor here? 4. 4 divides 1024 and 4 divides 52. Right? There is no other integer that is larger than 4 that divides both of those numbers. Okay? Now I don't want to focus on the algorithm itself. What I want to focus on here is the input. There are actually 2 inputs. Right? Which one do I look at? All right. So what if I made this a little bit more contrastful here? 1024, 44001, and 2, right? Now, which one of those is going to have more of an impact? The larger one, right? So if they're both numbers, then we're going to choose the larger, right? Because here's another reason why, at least in this case, GCD of AB, right, is equal to the GCD of BA. It doesn't matter which one you look at first. The larger one, that's going to be the one that influences it most, okay? So in this case, we're going to choose the larger. Come over here, and there we go. All right. So Euclid's GCD algorithm, we have 2 inputs. Right? There we go. All right. And here's a nice mathematical term, W log. Right? Anybody know W log? Right? Does anybody know what that acronym stands for in math? Without loss of generality. Right? So consider only the larger of the 2 inputs. Right? And that's because you can always switch them around, right? If B is the larger input and A is the smaller input, okay, we'll just consider the first. Now just switch them around, and now the larger one is the first, right? Because it doesn't really matter what the order is, right? You're still making the same number of computations. In fact, in the actual GCD algorithm, if they are reversed, I think that the first iteration actually reverses them back, so that the larger one is always the first one. Right? Okay. The second step, identifying the input size. And again, this is mostly obvious in most cases, but it's subtle, but it's very important, and it sometimes might be tricky. Right? So there are obvious examples. Right? For example, a collection. A collection size is the number of elements in the collection. Right? Right? What if we were looking at a matrix, say an n by m matrix? Right? That's a little less obvious. Right? This is less obvious. Right? Because n and m, those are 2 different values. Right? It has n rows and m columns. Right? So again, W log, without loss of generality. Suppose you can consider the larger value. Right? In other words, assume that n is greater than or equal to m, and focus on n. Right? That's it. That's a simple compromise. There's another solution to this, though. Right? Without loss of generality, suppose that n is equal to n c dot m. There we go. So I'm doing some math now, right? And then use n. Big N as your input, right? And we're actually going to do that trick later on for an actual example, right? Why? Because if you look at a matrix that's an n by m matrix, how many elements are in there? N times m. Well, just give that a different label, right? All you're doing is changing the parameter, that there are n element, big N elements in there, right? The really tricky one is what happens when you only have a single number, like Euclid's GCD algorithm. Or here's a number, tell me if it's prime or if it's composite, right? A single number integer n, what is the size of that single integer? Right? What do we mean by size here? Okay. So for example, say that our number n, right, is equal to 10, right? And then on a different input, say n is equal to 10,000, right? Is there a size difference between those two numbers? Yeah, most definitely. If you don't think that there's a size difference between those two numbers, let's exchange. You give me, I'll give you $10 and you give me $10,000, right? There's definitely a difference there. But what is the difference? How do you quantify the difference, right? So the question here is, what is the size of a number's input? Now, one answer that you could give is, well, I know computing, right? I know integers. They're all 32-bit numbers, and you could say, oh, it's 32 bits, right? Or it's a floating point number, a double. Oh, it's 64 bits. Again, that's a particular piece of hardware. Integers, by the way, don't have to be 4 bytes. All right? They don't have to be 32 bits. In fact, if you're programming in C, the only thing that C requires is that integers are at least 2 bytes, right? Usually they're 4 bytes, and long integers are 8 bytes, right? And so you can grow your numbers, but that's not the real answer. Right? All right, well, we already have an intuition here, right? That number is small, or that's smaller, I should say, compared to this number over here. Larger. Right? Now, what about them makes what about 10 makes it smaller than 10,000? Right? I mean, the straightforward answer is, well, it's obvious. They're smaller, right? But you have to think about how you quantify numbers, right? If I were to write these down in a different system, what would it be? Say, Roman numeral X, right? And over here, 10,000, how do you write 10,000 in Roman numerals? Does anybody know? I don't know either, right? So let's go with a different system. This is called a unary system. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So these ticks right here, right? If I were to do the same thing over here for 10,000, do you want to sit here and watch me do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10,000 times? No. Right? That's why we don't write them in unary. We write them in, these are called decimal, right? Or a computer does it in binary, right? In other words, the size of an input of a number is the number of, not characters, but number of symbols required to represent that number. All right, so n is equal to 10. How many symbols did I write down to represent that number? 2. That's the size of that input. What about 10,000? We're not counting commas there, right? That's just a visual aid. Right? So there were 5 characters, right? That's smaller, that's larger. Right? In other words, what we're actually talking about here is the magnitude. Right? Now, when we come back on Friday, I'm going to show you how to mathematically quantify that. It's something that you've used for many, many years, right? But you probably never were given a proper explanation of what it actually quantifies. Right? You're just told, here are some identities. Right? You need to know them for some reason. Well, now I'm going to give you a reason to know them on Friday. Right? And spoiler alert, it's logarithms. Right? That's what I'm talking about. Right? All right, we'll talk about that on Friday then.